Hi everyone, and this is Group 5's project on mirtazapine. My name's Bradley.
And I'm Radhika, and today we'll be talking to you about mirtazapine.
So Radhika, what actually is mirtazapine?
So mirtazapine is a drug used commonly in the treatment of depression.
Oh, but what is depression?
So depression is feeling unhappy and hopeless over a long period of time. The common symptoms of depression include the loss of enthusiasm, fearfulness, and increased anxiety.
So what is the biology behind depression?
Well, there are three main neurotransmitters involved. These include serotonin, norepinephrine, and dopamine. From this diagram, it shows the effects that each neurotransmitter causes. It is evident that all three neurotransmitters have a common cause of having a depressed mood. There are many theories regarding the causes of depression, but the main theory is the monoamine hypothesis.
So what does this show?
It showed that depression results from a deficiency in norepinephrine and serotonin. These deficiencies can be reversed through the use of an alpha-2 adrenoreceptor antagonist such as mirtazapine. The serotonin receptor that is used in mirtazapine is 5-HT. If this receptor is inhibited, then it reverses the therapeutic effects of the treatment that antidepressants have with serotonin reuptake inhibitory activity. Norepinephrine reuptake inhibitors stop norepinephrine from going back into the cells in order to improve the energy of the patient. If these inhibitors are blocked, it can trigger suicide, which is not ideal, especially with depressive patients. Therefore, this showed that drugs that selectively inhibited serotonin reuptake would produce better treatment for depression.
Ah, that makes sense. Now let's talk about the structure of mirtazapine. As you can see, there is an aromatic group and a pyridine group.
But wait, is that a tertiary amine there?
Yeah, it is. Mirtazapine also obeys Lipinski's rule of 5. It has a molecular weight of 265.35 and a log P of 2.9 to 3.29 depending on experimental properties. There is also no hydrogen donors and 3 hydrogen acceptors.
So, where are these hydrogen acceptors?
They're on the 3 nitrogens shown.
So how was mirtazapine developed and discovered to form this structure?
Well, mirtazapine was originally known as the Org 3770. It is currently sold under the brand name Zispin in the UK. It was developed by Organon International in the Netherlands and licensed in 1994. Serendipity played a major role in the discovery of antidepressants such as mirtazapine. From this, the first generation of antidepressants were discovered by the altering of molecular chemical structure of antipsychotics. This then led to the formation of imipramine. A further change of this chemical structure led to the formation of second generation antidepressants, which lacked the side effects that the first generation antidepressants had. The design of mirtazapine follows the dual action concept. This concept shows that the effects of norepinephrine and serotonin receptions had a better effect on treatment when compared to the selective action of serotonin reuptake. But where did mirtazapine actually originate from?
Mirtazapine is a part of the tetracyclic class. It was originally discovered from tricyclics, which was further originated from antihistamines. Promethazine, which is an antihistamine, was initially discovered in the 1940s, along with other first-generation antihistamines.
Chlorpromazine was then derived from promethazine in the early 1950s. Chlorpromazine uses the chemical skeleton from promethazine and has the addition of a chlorine group and the removal of a methyl group from its side chain. Originally used as a sedative, it was later found to have neuroleptic properties which made it the first antipsychotic. Imipramine, which loses the chlorine group and exchanges the sulfur connection for the addition of 2 carbons to the ring, was investigated as an antipsychotic, but later was discovered to be the first tricyclic antidepressant, also known as a TCA. And finally, for carbamazepine, it has an amide group rather than its carbon side chain, and now has a double bond present in its central cyclic ring. Carbamazepine was also a tricyclic antidepressant, but was then founded as an anti-epileptic. A problem that arose for tricyclic antidepressants was that they caused cardiotoxicity and anticholinergic effects, for the examples of dry mouth and constipation. So, you said that mirtazapine was a tetracyclic drug. How were tetracyclic antidepressants first developed?
The structures of myanserin and mirtazapine were developed with the help of the concept of the rich pharmacological profile, which is the interaction with different monoaminergic systems. One of the first tetracyclic antidepressants, myanserin, was first developed in the 1970s. Although the chemical structures of mirtazapine and myanserin are closely related, there are considerable differences in their biological properties.
The main difference in chemical structure is an isosteric replacement of the aromatic methane group in myanserin with a nitrogen to give a pyridine ring. Mirtazapine is found to have a higher pKa value and has a better antihistamine properties when compared to mirtazapine, which in turn shows it has a weaker sedative antidepressant compared to mirtazapine. Mirtazapine is also 3 times weaker in polarity than mirtazapine and has a higher oxidation potential. This is because of the conjugated nitrogen in the mirtazapine, which is less negatively charged than the nitrogen in mirtazapine. This has then reduced the affinity of the alpha-1 adrenoreceptor and sufficient noradrenaline reuptake of mirtazapine.
Mirtazapine is currently marketed in Europe as an antidepressant, however, it is not yet approved in the United States due to its serious adverse effects of a granulocytosis causing increased vulnerability to infection and leukopenia. Mirtazapine, however, has not exhibited these adverse effects.
When comparing mirtazapine and mirtazapine against other tetracyclic antidepressants such as aptazapine and statistiline, we can see similarity in the structure, as shown. Both molecules have been shown to be more potent than mirtazapine. Aptazapine has been shown to have approximately 10 times more potency to the alpha-2 antagonism. This potency of aptazapine is linked with the pyrrole groups attached to the 7-membered ring. So Radhika, was the structural activity relationships the same for the tricyclics?
So, for tricyclic antidepressants, the pharmacodynamics and physiochemical properties of these drugs are heavily influenced by their substituents, newly attached heteroatoms or ring flexibility. The ring structure in the tricyclic antidepressants is not associated with its affinity to any of the receptors. The tricyclic structure could, however, contribute to a range of adverse effects on the central nervous system due to the increase in lipophilicity of the drug. The ring system in TCAs has also shown little significance on inhibiting norepinephrine and serotonin transporters. So Bradley, what does this diagram show?
Other antidepressants such as SSRI, SNRI and NSRI have different mechanisms of actions when compared to mirtazapine. The diagram on screen highlights the actions of these antidepressants alongside mirtazapine. SSRI, SNRI and NSRI are all marked as green, while mirtazapine has been marked as an orange teardrop symbol. We can see that the serotonergic presynaptic nerve is responsible for releasing serotonin, as marked as ovals on the diagram, while the noradrenergic presynaptic nerve is responsible for the release of norepinephrine, marked as triangles. SNRI and NSRI drugs block the norepinephrine transporter, also known as NET, that controls the reuptake of norepinephrine back to the presynaptic nerve. This results in an increase of norepinephrine in the synaptic cleft. Similarly, SSRI and NSRI drugs block the serotonin transporters, inhibiting the reuptake of serotonin and increasing serotonin levels in the synaptic cleft.
So, do these drugs function differently to mirtazapine?
Well, mirtazapine blocks receptors in both the presynaptic and the postsynaptic regions. The presynaptic region includes the serotonergic nerve and the noradrenergic nerve. For the serotonergic nerve, mirtazapine blocks alpha-2 autoreceptors, resulting in an increase of serotonin levels. For the noradrenergic nerve, mirtazapine blocks alpha-2 heteroreceptors, resulting in an increase of norepinephrine levels. For the postsynaptic region, mirtazapine blocks the serotonin receptors known as 5-HT2 and 5-HT3. So what part of the structure is responsible for its pharmacological interaction?
Do you mean the pharmacophore? Using our gathered knowledge and comparing mirtazapine against other tetracyclic antidepressants, our hypothesized pharmacophore is shown. The pharmacophore contains an aromatic group, a methyl group, and the 2 key nitrogens. This chemical structure relates to other similar tetracyclic antidepressants as mentioned earlier. So how was mirtazapine then synthesized?
So, mirtazapine was initially developed from substituted piperazine, polycyclic piperazine, and tricyclic compounds. 2 methods were used for the synthesis of cyano-NMPP presented. Route 1 shows the reaction of an amine with the 2 chlorine groups under strong basic conditions, for the example of sodium amide. The second route shows the reaction of a chloride group with a secondary amine group. This is in the presence of heat and creates HCl as a side product. These reactions both produce cyano-NMPP through the nitrogen connection. Cyano-NMPP is reflux with potassium hydroxide with ethanol at 100 degrees Celsius for approximately 24 hours. After the 24 hours, carboxy-NMPP is created. This is highlighted from the difference in the cyanide side chain being changed to a carboxylic acid. Carboxy-NMPP is refluxed again, this time with lithium aluminium hydride and a tetrahydrofluorine, producing hydroxy-NMPP. This conversion can be seen from the carboxylic acid being changed into a methyl alcohol side chain. And finally, the product hydroxy-NMPP is treated with sulfuric acid at room temperature. This then forms the cyclic ring in mirtazapine. So that was a lot of chemistry we went through there. But Radhika, what actually are the side effects of mirtazapine?
The blockade of histamine H1 receptors causes the majority of mirtazapine side effects. Some of these are anxiety, diarrhea, and constipation. Patients should be warned about mirtazapine's effect on psychomotor performance, particularly driving, as drowsiness is a frequent side effect. Some research suggests that mirtazapine reduces insomnia, but it should not be used as primary treatment without the diagnosis of clinical depression. However, one of the withdrawal symptoms of this drug is insomnia. Therefore, a gradual reduction in dose is necessary to avoid this negative effect. It can also induce nightmares as it increases rapid eye movement.
So we've covered a lot of information, so let's recap. So in this video we've talked about depression and its biological basis, the structure of mirtazapine, how mirtazapine was developed and discovered, its SAR as well as its mechanism of action, the synthesis as well as the side effects. This concludes this informative video on mirtazapine, and thank you for watching.